In the next example, we're taking a look at finding the volume of a solid whose base is bounded by y equals the square root of x, y equals 0, and x equals 4. So the first step is to draw a picture of the base. I have that picture over here to the right with the square root of x drawn. Second step is to draw several segments in this base that are perpendicular to the x-axis. So these segments perpendicular to the x-axis have a length that will reach up to that curve. So each one of these lengths is equal to the square root of x. All right, so the height of one representative segment is the square root of x. All right, these segments are the sides of a square. So if you can imagine those squares coming up out of the base. Smaller ones closer to the origin, the largest one being a 2 by 2 square, since we're going to 4. Okay, the area of the square in terms of x will be the square root of x squared, which is just x. All right, find the volume formed by the solid whose side is bound by the region. If the areas of the cross-section perpendicular to the x-axis are squares or semicircles or isosceles right triangles. So if they are squares, the volume will be equal to the integral from 0 to 4 of x dx. If the cross sections are semicircles, the diameter of that semicircle is the square root of x, which means the radius of that semicircle is 1/2 the square root of x. The area of the semicircle is pi r squared times 1/2. Replacing r with 1/2 the square root of x, we're going to get pi eighths x as the area of one semicircle, with a dx thickness integrating from 0 to 4 will give us the volume. Okay, if we look at isosceles right triangles, that's just half of a square. So we can say it's 1/2 the integral from 0 to 4 of x dx. Okay, I'm not going to evaluate these integrals, but you should get 8 pi and 4 for the volumes after you integrate and evaluate. All right, in part E, it says what would change if the cross sections were perpendicular to the y-axis instead of the x-axis. So let's take a look. We're going to cut off that region at 4. Okay, so if the cross sections are perpendicular to the y-axis, here are just a couple representative lengths. These lengths will have a dy thickness. So this time I need to write the integrand in terms of y instead of x. All right, if we actually repeat it for all of them, not just the squares, so A was square, and B was semicircle, and C was isosceles, right? Triangle. We'll write the integrals for each of those. So, knowing that we need well, let's take a look at what would our lengths be. Okay, this first length right here is a length of 4. This second length is less than 4 units long. It's 4 minus some x value. That x value coming from the x-axis over. So here's some x value. And I want the red distance, not the blue distance. So I need each of these red segments to be 4 minus x units long. But we also know we want to write our lengths in terms of y and not x. So if we solve the equation y equals the square root of x for x, we'll get y squared equals x. So now I can say the length is 4 minus y squared. Okay, so for the square, the volume, if we have squares on as cross sections, the volume would be the integral from 0 to 2. Notice those are the y values because we're integrating in terms of y. Of the integrand 4 minus y squared dy. If we're going to do semicircles, our volume is going to be the integrand from 0 to 2 of pi eighths 4 minus y squared. So the reason why it's pi eighths is because I had to take 4 minus y squared, multiply by a half. That's my radius, and I'm going to square it. So I think I need my square down here as well. Okay. Then the isosceles triangle. Volume is equal to 0 to 2, integral of 0 to 2. And the isosceles triangle is just half the square, so I'm just going to put a half out in front of 4 minus y squared dy. Okay, let's look at question 2. I didn't evaluate those. Setting up the integral is more important, but we could evaluate for the numerical volume. Let R be the region bounded by the graph of y equals x squared and y equals 8 minus x squared. Okay, so roughly, we'll call this x squared, and we'll call this 8 minus x squared. Okay, we need to know where those two graphs intersect. And it's going to happen at -2 and +2 when the y value is 4. Okay, so let the region bounded by these graphs be region R. Find the volume of the solid that has R as its base if every cross-section is perpendicular to the x-axis and is a semicircle or equilateral triangle. Okay, so remember, draw a representative length. These lengths will have a dx thickness, so we want our integrand in terms of dx. If they're semicircles, those lengths, well, let's define that length. That length is actually going to be 8 minus x squared minus x squared, or 8 minus 2x squared. So that's a length. Now for the semicircle, we need half of that. So 4 minus x squared will be the radius. All right, we're going to do pi halves, the integral from -2 to 2 of 4 minus x squared dx. Oh, I got to square the radius again. I keep forgetting to square the radius. So there we go, 4 minus x squared, quantity squared. All right, to integrate that, probably best just to expand that and integrate. Okay, last one is equilateral triangle. The length of the side is the base of the length of the side of the equilateral triangle, so square root of 3 over 4, 8 minus 2x squared squared. That's the area of one equilateral triangle. We're going to integrate from -2 to 2, and that will give us our volume. Okay. That's a good introduction to the volumes by cross-sections.